Hey guys, welcome back to another round of chemistry notes. In this video, we are going to talk about intermolecular forces. Before we can talk about intermolecular forces, though, let's just review intramolecular forces. These are the attractions within particles. They result, I know your notes say results, it should say results, when electrons are lost, gained, or shared to form a bond. So there are three major types. These are what we've been talking about for the whole unit. This is ionic bonding is an intramolecular force. Covalent bonding is an intramolecular force. And metallic bonding is an intramolecular force. And intramolecular forces, the forces that hold individual molecules together, can be broken and formed during chemical processes only. There is no physical process that can do this. Boiling, freezing, evaporating, condensing, none of those can break an intramolecular force. Those are what we've talked about so far. What we're going to talk about now that is new are intermolecular forces. Intermolecular forces can be abbreviated as IMFs. And these are the attractions between different particles, from one water molecule to another water molecule, from one sodium chloride crystal to another sodium chloride crystal. These can be broken and formed during physical processes because intramolecular forces, the ones that hold individual particles together, are much stronger than intermolecular forces. So you want to think of the children here. So imagine, and I know that many of us don't play Red Rover anymore, but imagine you're playing Red Rover, right? You've got this line of kids together, they're all holding hands, and you try to break them apart. This right here, holding these two kids together, this is going to separate a lot easier than the bond holding this child together. So in Red Rover, if you don't know, you basically run full speed at a line of people and try to break between them. And when this happens, you are much more likely to separate this right here than to cause one student to just, explode into like a million pieces. Because the bonds holding this person together are way, way stronger than the bond holding these two people together. So the intramolecular forces, the forces within one single particle, are a heck of a lot stronger than the intermolecular forces, the forces holding different particles together. There are three types of intermolecular forces that you need to know. The first and weakest, this is your weakest one up here. The first and weakest is London dispersion forces. That can be abbreviated as LDFs. It is also called van der Waals forces. They are all the same thing. And this occurs in all molecules and atoms. All of them. Nonpolar, polar, all of them. Because there's no specific requirement for this to happen. The requirement is that you have to have electrons. And everything has electrons. So how LDFs work is every atom, every molecule, every ion, whatever, has electrons in it. So you've got like your nucleus here, and you've got all of your electrons just swirling about throughout the atom, flying all over in no particular order, all completely independent of each other. So every once in a while, completely randomly, for no real reason other than they're just moving, eventually you'll have more of your electrons ending up on one side of your atom. Again, completely randomly, and it only lasts for a split second. But in that moment that you've got more electrons over here, this side of your atom or molecule or whatever is going to be more negative because it's got more electrons. And this side is going to be more positive because it has fewer electrons. And as we've been talking about all semester, opposites attract. So now we've got a positive end of this molecule here because it doesn't have that many electrons. So the electrons in this molecule are going to be attracted to that. They're going to sort of fly over to this side of this molecule and cause this end to be negative. And as a result, this end will be positive. So your LDFs are this attraction right here. This side of this molecule is positive, and it's attracted to this negative side of this next molecule. This attraction right here is your van der Waals force. It's your London dispersion force. It is caused by something called an instantaneous dipole. Remember, a dipole is having like a positive end and negative end. We've seen it in our polar molecules. Well, this can happen in nonpolar molecules. It causes a dipole, a negative end, and a positive end, but it only lasts for just a very short, very brief moment. And then it's gone. It's instantaneous. So this is a lot weaker than all of our other forces because it's caused entirely by chance. It just happens every once in a while the stars align correctly, and we'll end up with this instantaneous dipole causing these molecules to be attracted to each other. Because it is caused by the electrons and the movement of the electrons, the more electrons that you have, the stronger this force is. So if you had something like H2, this is two hydrogen atoms bonded together. They have a total of 2 electrons between them. That's going to be a very weak dispersion force because it does not have very many electrons. If you had 2 glucose molecules, which are C6H12O6, there's a lot more electrons in this molecule. You've got 6 carbon atoms bringing their electrons and 12 hydrogen atoms bringing their electrons and 6 oxygen atoms bringing their electrons. There are a lot more electrons here to cause this instantaneous dipole. It's going to be much stronger. So the dispersion forces between H2 and glucose are not the same. The more electrons you have, the stronger the dispersion force. Generally, though, even a quote-unquote strong dispersion force is going to be weaker than the rest of these forces. Your sort of middle ground, IMF, your medium strength, is dipole-dipole. This is between polar molecules. It's pretty much the same thing as your dispersion forces, but it's between permanent dipoles. It's between dipoles that already existed as a result of polar bonds, not something that has to wait for electrons to move correctly. So for example, this is like our formaldehyde molecule. This is like a carbon here and an oxygen here. This bond between carbon and oxygen is a polar bond, which means this molecule is a polar molecule. It's always going to have a negative end and a positive end. So when you put it next to another formaldehyde that always has a positive end and a negative end, you're going to have the same positive to negative attraction. But since this dipole is always here, this attraction is always here, it doesn't depend on the random motion of electrons, it's a little bit stronger because it's more dependable, because it's always here. And then there is one special type of dipole-dipole that is so strong, it sort of gets its own name, its own category, and that is hydrogen bonding. Notice bonding is in quotes. We'll talk about that in just a second. This is your strongest type of IMF. It basically comes from a very, very strong dipole. This can only occur in molecules containing hydrogen bonded to either fluorine, which is your most electronegative element, or oxygen or nitrogen. These are your 3 most electronegative elements. These are the only ones capable of causing hydrogen bonding. So it's the same idea as up here. The negative end of one molecule is attracted to the positive end of another, but it just takes it to extremes. So here we've got water. We've got our oxygen in the center bonded to hydrogens. And this oxygen is super, super electronegative, which means it's taking way more than its fair share of the electrons in this bond. It's not ionic, it's not stealing them, but it's definitely getting close. It's very strong. It's really hoarding those electrons. So it is very partially negative, and this is very partially positive, and this is very partially positive. So we've got this attraction here between something very, very negative and something very, very positive, and that causes an even stronger attraction than in just mildly negative and mildly positive. Again, these are not full charges, because then it would be ionic and it would be an intramolecular force. These are still partial charges. They are not entirely positive or entirely negative, but they are much stronger than a regular dipole, which is why we give this sort of its own name. let's talk a little bit more about hydrogen bonding. All right, so hydrogen bonding, and again, it's more like bonding, is the force of attraction between the hydrogen atom bonded to a highly electronegative atom, fluorine, oxygen, and nitrogen only, and the electronegative atom of another molecule. That's a little confusing. What it means is if you have, say, hydrogen bonded to fluorine here, this is the whole molecule, hydrofluoric acid, you're going to have an attraction draw two molecules here, you're going to have an attraction between the hydrogen atom in this molecule and the fluorine atom in this molecule. And this attraction here is the hydrogen bonding. It happens between two different molecules. It's intermolecular, like international is between two different nations. So a little bit more about hydrogen bonding. It is not a real bond. It's not intramolecular, so hydrogen bonding is a bad name for it, but it is what it is. We show it with a dotted line, and it's a dotted line between the two different molecules. So back here, you can see in this picture, we've got this dotted line here between our two water molecules. That's the hydrogen bond. The dotted line is the hydrogen bond. And it is responsible for the unique properties of water. Surface tension, expanding when it freezes, all that good stuff comes from hydrogen bonding. All right, so here you can see, and we're going to talk about boiling point a lot more in just a second. We've got a bunch of different elements bonded to hydrogen, and we've got their boiling points plotted. So here we've got carbon, silicon, germanium, and tin all bonded to hydrogen. That's a lot of your elements in group 4. And as we move from, this is the bottom of the table, period 5 to period 4 to 3 to 2, the boiling point decreases, gets easier to boil. And then again, we've got iodine bonded to hydrogen, and then bromine, and then chlorine. And again, it decreases as we move up the table, and then it shoots up here to fluorine. Fluorine boils at a much higher temperature. That's because this has hydrogen bonding. And again, antimony to, arsenic to phosphorus, and then nitrogen shoots up because nitrogen can hydrogen bond. And of course, water can hydrogen bond as well. So this weird interruption of the trend where instead of decreasing, it suddenly increases, that's because of the hydrogen bonding. So real quick, before we talk about boiling point and hydrogen bonding, let's do a couple of examples here. We're going to draw the Lewis structure. We're going to name the molecular geometry, the bond angle, the molecular polarity, the types of IMFs. We're also going to draw the dipole if that's appropriate. So our oxygen molecule at this point, hopefully you can do these pretty quickly. We've got oxygen double bonded to another oxygen, and each oxygen has 2 lone pairs. If you still need to draw that out in stages with your individual Lewis structures, do that. But at this point, I'm going to try to assume that y'all are pretty on board with the Lewis structures. So if you have 2 atoms bonded together, there's exactly one way to do that, and that is with a linear molecule. And if it's linear, that means our bond angle is going to be 180 degrees. Here we've got 2 of the exact same atom bonded together. There is no difference in electronegativity between this oxygen and this oxygen. So as a result, this is a nonpolar bond. And since this is a nonpolar bond, the molecule as a whole is nonpolar. Since it is nonpolar, the only types of IMFs it can have are dispersion forces, LDFs, van der Waals. Again, all same versions of the same thing. That's all it can have. You cannot have dipole-dipole if you are not polar, and you definitely can't have hydrogen bonding. All right, let's take a look at our next one here. We have BF2H. First, we need to figure out our central molecule. Well, it can't be hydrogen, because it'll never be hydrogen. We have 2 fluorines and 1 boron, so it makes sense to put boron in the center, and then we will bond each of our fluorines and our 1 hydrogen. Don't forget your valence electrons on these fluorines. And again, boron only has 6 electrons, but that's what it's supposed to have. That's how we know we've done it correctly. So our molecular geometry here with 3 bonding groups and no lone pairs, that's going to be trigonal planar. which is going to have a bond angle of 120 degrees, and 360 divided by 120, pretty easy one. Then we need to check out our molecular polarity. Again, there are sort of stages you can go through to see if your molecule is polar. First, look for lone pairs on your central atom. There are none. Since there are no lone pairs on our central atom, we need to look at our terminal atoms. Are they all the same? No, they are not. Here we've got a polar bond between boron and fluorine. So we've got a dipole sort of doing this on this bond. And here we've got boron bonded to fluorine, so pointed this way. And here we have boron bonded to hydrogen. If this was another fluorine, all of our dipoles would cancel out because all of our terminal atoms would be the same. But they are not all the same. These two are different. So we've got electrons being pulled up and to the left. We've got electrons being pulled straight down. As a result, we're going to get a dipole pointed right between them. If you've learned what a vector is, this is the resultant vector of these two vectors. So we're going to get a dipole pointed down and to the left, and this will be a polar molecule. So our types of IMFs here will be LDFs, because always there are LDFs. And since it's polar, we can also have dipole-dipole. And this is called dipole-dipole, not because of this dipole and this one, but because if we had another molecule just like this, its dipole would line up, pointed the exact same direction, and we would get an attraction between this dipole and this one. And this attraction right here, that is the dipole-dipole force holding these molecules together. So this would be another B, F, F, H. And this attraction right here is the dipole-dipole force. All right, you've got a little bit of practice in your book, some multiple choice, some drawing in the Lewis structures and the dipoles. Go ahead and work through those. Check your answers on my website to make sure you've got it. And when you're ready to move on, unpause the video and we'll talk about how to measure IMFs. All right, there are two ways of measuring intermolecular forces, and they are going to sound very similar, but they're not actually the same thing. There's one very important difference between them. The first way of measuring IMFs is with vapor pressure, which is the pressure exerted by a gas, or a vapor, when it is in dynamic equilibrium with its liquid. We're going to talk about dynamic equilibrium a lot more in the spring. What I need you to know right now is that this just means the overall amount of vapor in a container, and it must be a closed container, is not changing. So you start by just dumping a whole lot of liquid into a container. It'll start to turn into a vapor. That's just what liquids do. And eventually you will reach a point where liquids are turning into vapor molecules at the same rate that vapor molecules are turning into liquid molecules. That is dynamic equilibrium. The amount of vapor in the container at that point, whether it's like a whole bunch of vapor molecules or just like, one vapor molecule, is going to be determined by the intermolecular forces. If you have a stronger attraction between your particles, that means that fewer particles are going to escape to the vapor phase. If all of these molecules are so attracted to each other that they're like super glued together, you're not going to get any vapor molecules. No vapor molecules means there's nothing creating pressure and you have a really low vapor pressure. Versus, if these are not attracted to each other at all, they're all going to fly into the vapor phase and you're going to get a ton of vapor and a ton of vapor pressure. So, putting this a little bit more succinctly, as you increase the strength of your IMFs, as you go from dispersion all the way to hydrogen bonding, as your intermolecular forces get stronger, your vapor pressure is going to decrease. More IMFs, harder to separate your molecules, less of them escape to the vapor phase, lower vapor pressure. That's the first way to measure your IMFs, is with vapor pressure. The other way is with boiling point, which also has to do with liquid versus vapor, but it's a little different. This is the temperature at which molecules separate from each other in the liquid phase and enter the gas phase. So this also depends on the attractions between your particles. If you have a stronger attraction between your particles, they're going to be harder to separate. If they are harder to separate, you're going to have to put more energy in to separate them, which means you're going to have to keep adding heat to make them enter the gas phase. You're going to have to make it hotter and hotter to make it boil. So as you increase the strength of your IMFs, you are increasing the boiling point because you have to add more and more energy to make it boil. Higher IMFs, higher boiling point. So this is a direct relationship versus IMFs and vapor pressure are an inverse relationship. They are indirectly related. All right, that is it for things to learn here. Next in your book, you have a whole lot of practice. You've got multiple choice practice, you've got Lewis structures practice, you have free response practice. All of those keys are posted on my website. So go ahead and work through that practice, check your work, and congratulations, you've made it through the last video for Unit 6. All that is left in this semester is to pass the fall exam. Do your very best on that. So, as always, good luck and happy studying.